All right, so we're going to look at exponential growth. And this is basically the idea is a lot of things we're going to look at in this course grow exponentially. So it's good to be able to be familiar with how this works and a little bit of the math. I will say that this is probably the most mathematical thing we're going to do this whole quarter. Kind of ironic we do it right away, but just sort of keep that in mind. Now, exponential growth, we're going to look at it in a couple different ways, but we're going to start just by this taking on one hallmark of this. And one hallmark of exponential growth is that the time it takes to double in size, or the doubling time, is constant. And so that basically means that whatever you're talking about, if it doubles every 2 years, it's going to double every 2 years, and it's going to consistently keep that way. And there's this rule of thumb that we'll use, and we'll go through and kind of show how this works and why this works. And it's called the rule of 70. It says the doubling time associated with the percentage growth rate is 70 divided by that percentage rate. And so this can look at many different things, but let's just say, for instance, you're looking at your savings account, and say that your savings account has a percentage rate of 2% every year. And so what you do then is you take this 70, divide by that 2, and whatever money you initially put in to that savings account should double in 35 years. So again, we'll show you, how this works in a little bit, but that's just the rule that we're going to use. We're going to kind of go back to this a lot, so it's an important thing to kind of get your sort of, kind of understand. And then, even though we'll do a lot of this in terms of years, this works for any time scale. So they point out here, the author does that, for pandemic cases. For instance, if there was a growth rate of cases of 3.5 per day, the doubling time would be 20 days. And so it's just whatever sort of time frame you want to use. So the example we're going to kind of keep going back to is from the book, and it's just the population. And so they're saying, suppose the population of a city doubles every 10 years. And so there's a couple ways we can do this. And we're going to try to explore each one now. The sort of basic way is just to kind of just start doubling it. So we're saying it starts at 1900 with 100 people. So 1910, 200 people. 1920, 400. 1930, 800. 1940, 1600, and we can keep going on, but we don't, and we'll leave that as an exercise for later. But what we do say is that, okay, so after 100 years, so the year 2000, the population then will be 100,000 to 100,000. I can't say this. 102,400. And so let's look at this a little bit. So to add some math to this, we're going to use this equation here, and so we're going to use 2 we're going to call it some sort of power to the n. And this is sort of our definition of how population growth or exponential growth works. And so this formula here, now the term exponential itself means some power. Here we're using 2 raised to some number. And so here, in this case, this m here will be what we call the multiplicative scale. And then n is the number of doubling times. And so, for instance, this, if I do 2 doubling times, then this would be, this equation would come out to be m is equal to 2 to the 2 power, which is 4. And so our m would be 4. And so what we would do is we'd take our number of people, 100 people, and multiply by 4. And we get, 400. That'd be 2 doubling times, and of course we have that on the little scale here at 400. Okay. And so what we'll do, because we'll typically be looking at time scales of years, is we'll take this and that exponent that we're talking about, the 2 to the exponent, we'll write it as t over t2. And so this is just a definition. T2 is the actual doubling time. And then t is the time that we're talking about. And the m is still that multiplicative constant. Okay, and then so we can take this, and so for us here, our particular situation, this equation would be m is equal to 2, t divided by 10 years. So 10 years there, right? And so that would be what that would look like. And so, for instance, we can take this equation and just kind of do what we just did. So in 20 years, so I'll put 20 years up top divided by 10 years. The years cancel, and I get 2 to the 2 power, which is a multiplicative constant of 4, just like we had, a second ago. And so that, again, works out. It's just sometimes it's nice to have this equation. For instance, this one here, you can actually double it, a whole bunch of times to get to this crazy number here. But another way you can do that is take this, 2. So instead of 100 or 20 years, write out the 100 years. So 100 divided by 10. So I get 2 to the 10 power, which if you plug into your calculator, when I did it, I got 1024. And so again, just like last time, what that means is we take that number of 100 people and multiply it by that constant m. And when I did that, I got this number that we're looking at, 102, 400 people. Okay, and so that's one way to approach this problem. There's also another way that we'll talk about now. Now, another way to do this is to look in terms of another equation. Again, it's still the same way, so it's still exponential growth. But now what we do is we write in here 1.07, and then n is the number of years, or number of times that this happens. And so we're thinking this more in terms of an interest rate. And so from our rule of 70, we know that it says 70 divided by the percentage rate equals the doubling time. And so with this city, the doubling time is 10 years. Then if I take this, I can get that the percentage rate will be 70 divided by 10, which is 7. And so what that means here is we have a percentage of 7, and so basically every year the number of people grows and turns into 1.07 times that initial number. And so after 1 year, you'd be at 1.07. After 2 years, 1.07 times 1.07. And so if we take this, what happens is 1.07. So again, our understanding is that after 10 times, after 10 years, we should end up being at that doubling point. And so if you take your calculator and do 1.07 to the 10 power, I get 1.967 as the multiplicative factor. So again, it's roughly doubling. It's not perfect because this rule is a little bit of a fudge, but it's just a really good rule of thumb. But hopefully you can follow that, and that makes sense. It's another way to kind of think about it, and the book does an example using percentage rates, which you might want to look at. Okay, so now we're going to look at what's called the natural exponential function. I should cross this out. So this one here is exponential function. Sorry about that. And that's this guy here. You might have seen this, you might have not. And basically the way that it works is there's a special number, and it's 2.71828. And for reasons that have to do with calculus, which doesn't really interest us too much, if you take this particular function, this number to the x, it just helps some of the calculus formulas be a little bit easier. So it's just something that's just kind of easy to use, but really it's nothing new that we've been doing. It's just taking some number to the power, just that number happens to be kind of a funky, ugly one. And here's a graph of this. Again, this is a really famous one. You can find a lot of stuff online about this. And so this is just a plot of this. And again, it just shows you that, just like we expect, is this something that just, starts to increase rapidly, which is, again, one of the characteristics of exponential growth, right? And so here, to make this plot, you literally, so you can just look at that and plug in, so at 0. So e to the 0 equals 1. So you have this point 0, 1. That's the first point. And then e to the 1 would give us that number, 2.78. So that's the second point over here. You can just go ahead and make this plot, and then e to the 2. Again, you can plug in your calculator too if you want. When I did e to the 2, I got 7.38. So you can see these sort of points here on the plot. And so it's just exponential growth, and it's just a special function that we're going to use. Now, the exponential function is the type of function that has an inverse function. This inverse function is called the natural logarithmic function. So I have these titles backwards. Again, sorry about that. Logarithmic. And so this is natural log of x. And the way that it works is that if y is equal to the exponential of x, then the inverse will work out sort of the opposite way. It'll work out that then that natural log of y gives us x. And so basically, if I do e to the x, it should give us y, and the natural log of y should give us x. And so it's something you should try with your calculator, make sure it makes sense. But what that means for us is that we have this relationship here, that the exponential of the natural log of x gives us x. This is something that we're going to use. It's just kind of handy. So like I said, I would give this a try, but it's really, just a little trick we're going to do to kind of make this stuff work just a little bit easier. All right, and last step before we go through and sort of prove this rule of 70, and this is just a kind of a math thing. So just take a second here and look at this problem. We want to know is what is 3 to the 3rd power to the 4th power equal to? Is it 3 to the 7th power or 3 to the 12th power? Okay, so give us a try. All right, hopefully you got 3 to the 12th power. A couple different ways to think about it. First of all, you can just sort of plug this into your calculator. So 3 to the 3 to the 4th power. If you do 3 to the 3, you get 27 to the 4th power. And when I did that, I got some huge number like 5.31 times 10 to the 5th. And you can show yourself that if you do 3 to the 12th power, it comes out to be this too. So that's one way to think about it. Another way is, what is this writing us? Well, this is basically saying 3 times 3 times 3 to the 4th power equals something. And so what that really is, it's going to be, 4 sets, 3 times 3 times 3, 3 times 3 times 3, 3 times 3 times 3. Same thing, which you can see is 12 threes. And so it's 3 to the 12th power. So we're going to use that just for this proof here. All right, and so we're going to try to go through and, again, prove this notion that we've been talking about of the rule of 70. And so I'm going to start out here with this relationship right here. So m is equal to 2 to the t over the doubling time. And what I'm going to do is I'm going to write 2 in a really special way. I'm going to write an e to the natural log of 2. Again, when you do e to the natural log of whatever, it equals that whatever. And so I can plug it in over here and get e to the natural log of 2. So that's where I plugged in for that 2, and it's still to the t over t doubling time power. And again, just from what we just talked about, though, when you have something to the power raised to the power, you just multiply those two powers together. So it's e natural log of 2 times t over t2. Now, we generally write this way just because it's a little bit more pleasing to the eye, but it's the same thing. So I just kind of distributed, moved the t over here since the order of multiplication doesn't really matter, and then kept the divided by t2 over here. Okay, so I did that with this formula. Now what I can do is a similar thing with the other one. And so this is the b to the n power. I'm just going to write it here, b to the t. And so we're going to assume that we're talking about sort of each time as another year that we're kind of looking at there. And so I'm going to do the same kind of thing here. I'm going to write b as e to the natural log of b. And so I put that in here, e to the natural log of b raised to the t power. And of course that is just those two things multiplied, and so I'll write it as t to the natural log of the b power. And so these are the two equations that we've been using. And then finally, what have we been using for the b? Well, we've been using some sort of a percentage rate, like 1.07. And so I'm going to write this as 1 plus p, where that p would be that 0.07. Okay, so again, it's just kind of a mathy thing that we're doing just to kind of express it in a way that's going to make it easier for us to look at in the end. And so here I'll write this as e to the t, and then this will be natural log of 1 plus p. So we got these two exponential ugly looking things, but they equal the same thing, this m. So what we're going to do is we're going to go ahead and set those two things equal. And so what's that going to look like? Well, it's going to look something like this here. It's going to be, e to the t natural log of 1 plus p. Then that's going to equal e to the t natural log of 2 divided by that t to the doubling time. All right, and we have an expression like this, exponential to something equals exponential to something. We can just set these two exponential pieces equal. So it's like t natural log of 1 plus p equals t natural log of 2 divided by that doubling time. And what's nice is we can then cancel out these t's, and we have this equation that basically we can go through and solve for the doubling time. And so we can actually rearrange this a little bit to get t2 is equal to natural log of 2 divided by natural log of 1 plus p. I should probably point out that I would never ask you to kind of do this proof, but I think it's kind of a nice thing to go through and do. Now, this thing here, it turns out that the natural log of 1 plus p, all right, when p is small, is pretty close to just p, like that there. Okay, and so now what can we do? Well, we can go through, and this basically now gives us an equation to solve for this doubling time. So what did we say? Well, for this example that we were looking at, the thing that doubles every 10 years, right, we said that it had a percentage rate of about 0.07. And so if I go over to here and look at this, natural log of 2 divided by, again, 0.07, if you plug that into your calculator, and I'll just even go a step further, just cancel this out. So that natural log of 2, if you plug it in, it comes out to be 0.693, which is pretty close to 70. And so when I did this, I got 9.9 as the number of years that we're talking about there. And so again, this is how you derive that kind of rule of 70. So it's basically whatever your percentage rate here is divided by this over here. And again, like we said in our example, this leads to a doubling time of 10 years. Okay, and so just to kind of reiterate here, what we have then is we have these sort of two different versions of this equation. So m is equal to these two equations that you can basically use one or the other. Sometimes maybe you can even use both to double check, but that help you actually calculate this exponential growth business. And so it's that 2 to the t divided by the doubling time, and then the other way is 1 plus p, where that's your percentage rate, with then this t being years if your percentage rate works every year. And so there's an example in the book that kind of summarizes all this, and so I think at this point, so it's example 1.1.2, and it's on page 7. So I would give that a look, and I think hopefully if you read through that and it kind of makes sense, then that can be a really good step. And then of course we'll talk much more in class about this. All right, thanks.